Yeah, good morning. I welcome you all back again after a break of 2 weeks. You had your CAT 2 examination and your Diwali celebration. Hope you all are been no good, keeping good health and no charged to this Diwali celebration holidays and refreshed, and you are back again on our learning phase, and you are prepared yourself for regularly attending all the classes and to go for another 1/3 of semester, almost one more month left for all your course to get over. Hope you will have the same energy level and the enthusiasm in learning. And I just want to recapitulate what we have done so far, and then we will proceed with the remaining part of our content of our course, vehicle dynamics. Right. So, of course, we have learned vehicle dynamics first from learning fundamentals of mechanical vibration. We have got a module specially to understand the basics of mechanical vibrations. So we started with the simple harmonic motion, and then we have gone into free and forced, damped, undamped, single degree freedom vibration system, and so on. And we are able to understand the basics of mechanical vibrations. And then we had started our vehicle dynamics course from vibrational models. That part of vibration models constitute in a vehicle dynamics course is what is called the vertical dynamics. That's otherwise called ride dynamics. So we have learned ride dynamics, where we have represented our vehicle to be a discretized lump to mass spring damper model, having two masses, unsprung and sprung mass. And we essentially looked at two important deterministic model. One is pitch and bounce model, another one is quarter car model. And we were able to get the natural modes of vibration under these two models. And we were able to find some insight of design aspects that go in to get a good ride aspects. And then we understood also the significance of the role of suspension in your quarter car model, wherein we could see there are three important requirement of suspension. One is, of course, the vibration isolation, and then the other counterpart is to have a road holding, where you should have a grip of your vehicle on the road, which should take care of your handling aspects of your vehicle. And the third requirement of your suspension is to have the travel space so minimum, so that you would have a rattle space maximum to accommodate your gadgets of modern control system of your vehicle, all in a safe manner between unsprung and sprung mass, between your axle and your body, to keep and ensure that the suspension would always fulfill its requirement. And continued with that, we also have understood what do you mean by passive system of suspension, active system of suspension, and we have understood the advantage of having semi-active suspension system. And we have looked at different case studies by varying the parameters, such as unsprung mass. If I vary, what would happen? If I vary the spring stiffness, what would happen? If I vary the damping coefficient of my shock absorber, what would happen? Studies all we did. And then this vehicle model essentially have to be done in order to understand what is called the human perception of vibration in a vehicle. So we have understood an important definition such as SAE, Genevieve's criterion, and ISO 2631 whole body vibration criterion highlights. And what are the necessary tests that are conducted in the vehicle to find out this whole body vibration perception. Those tests can be in the laboratory, or it can be on the test track. And the test track, we importantly look at something called the jury test to have a subjective measure of your vehicle. And then the necessary tests are carried out in the laboratory in order to map your subjective rating to the objective measures to lead our process to have a product development as a whole. So this what is that reason why we have looked at a vehicle as a mathematical model on one side, and we have also understood the human perception and the requirement and standards on the other side. Then we were ending our vertical dynamics, looking at real-time input. If I give to the vehicle, what would happen? So in such part of our ride dynamics, we have modeled our vehicle as a single degree freedom model subjected to a real-time road input. So there are something called road roughness index, and we were representing our road undulation, our road profile, our road texture as power spectral density function, and then we were able to get with the vehicle transfer function known from your single degree freedom model, we are able to find out what is called power spectral density function of your response inside the vehicle, and that was essential input for to find out your RMS acceleration. So this is what essentially we were looking at and finished nicely our ride dynamics part. And then we were entered into another important part of vehicle dynamics called the lateral dynamics. In lateral dynamics, we were looking at a vehicle governing equation on the ground plane, and those governing equation was deduced from the generic framework of vehicle if that would have been in a space. And we have essentially defined what you called body-centered coordinate system, which is essentially non-inertial frame of reference. And that is essential to account your governing equation of a body which could have 6 freedoms at space. And we were imposing necessary assumptions of our ground vehicle on the ground, and we were able to deduce the required equations for motion of your vehicle on the ground. And we were looking at systematically this governing equation from the elementary model, but most important model called the steady state model of your vehicle through a bicycle model. And the steady state equation is what is helping you to describe its motion and essentially to understand the tendency of a vehicle by a term called an understeer gradient. And we looked at what would happen to the understeer gradient if it is values less than 0. Then it is oversteer effect, and what is the condition of neutral steer. All we have looked at, and then we looked at pure cornering, where we just had developed our governing equation from the bicycle model and represented that as a state equation form. And that was helped us to further go in for finding out transfer function, steady state gain, or what do you mean by frequency response function, all to understand. And we have also looked at parallelly the various tests that are conducted on a vehicle called open loop test. Essentially, they are the vehicle test on the ground in a circular track. There are 3 tests, standard tests. One is constant speed test, constant radius test, and constant steer angle test. And all are essentially to understand the assumption in bicycle model, of course, is sufficient for to look at vehicle dynamics, particularly handling aspects in mid and high speed cornering. But in reality, if you look at the tendency of the vehicle get influenced by the design of your vehicle and the loading condition of your vehicle. This all to understand, we have to take, of course, real vehicle. And that's where the advantage of having some multi-body dynamic software like CarSim software all do have an advantage to really have your vehicle on the test track and conduct and see what would happen to your understeer gradient. So understeer gradient, what we have learned was only comes from the tire compliance, or that also from the linear tire model. And that we understood, then we were looking at an important design aspect like camber angle and its change, and then accounting importantly the role of suspension in the vehicle roll. So the role of sprung mass relative to unsprung mass do play an important role to have a steer action in your wheel. And that is to be accounted, and that has got a direct influence on your understeer gradient. So during hard cornering, there is a lateral load transfer. That lateral load transfer is responsible for to make a vehicle body to roll. So in bicycle model, we have not considered suspension, so there is no roll effect considered. But we have improvised that model by considering sprung and unsprung mass and sprung mass roll because of introduction of suspension that we consider. And we have seen, learnt the influence of suspension over an understeer gradient. And of course, you could have answered this CAT to the questions related to what all that I'm briefing now, so that it is complementing you. Now to recapitulate and have what we have learned so far in our vehicle dynamics course, that helps us to move forward further to learn in this course, right? And apart from suspension roll, also we looked at change in camber, what would be the effect on your understeer gradient, and what is the effect of your roll steer effect in your vehicle, and so on. And that is where we have just stopped our lecture. And there were 30 lectures so far what we have learned, listened to complete these two important part, ride dynamics and lateral dynamics aspect. Of course, lateral dynamics aspect is not over. We have looked at first part of lateral dynamics, where we looked at importantly steady state gain, and essentially to say what are the responses of your vehicle. But we have not learned or looked at the aspect of stability of your vehicle point of view. So we are going to have now on what is the remaining part is we are going to continue with our lateral dynamics, looking specifically on a vehicle stability analysis, and that stability analysis would be on ground plane as well as the suspension introduced model. So rollover stability. So these two aspects that we are going to study, and that completes vehicle stability. And then we have two important parts of our vehicle dynamics course. One is longitudinal dynamics, and another one is the tire dynamics part. So these are essentially the remaining portion, and we may be able to complete them another 12 to 15 hours of lectures. And I will be today introducing to you what do you mean by vehicle stability, and we will start our lecture, right? So do you have any questions or doubts in this part of summary? If it is not so, I'm happy that no, we are ready to go ahead, right? So let me share my screen to continue our today's class. So this is lecture number 31, and today's date is 8/11/2021, and we are going to continue with the vehicle stability. Just a minute. So when you say the term stability, you are immediately connecting your basics of equilibrium. So what do you mean by equilibrium? Correct? What do you mean by equilibrium? What do you mean by equilibrium? So you can have an equilibrium called a stable equilibrium. So look at this simple system. I have this curvature, and inside this curve I have a sphere. And if I disturb the sphere, this would oscillate and settle down. And this is ensuring an equilibrium state of the sphere motion, the oscillation, and then it will settle down at the same location. Even I disturb it and then remove the disturbance. And this equilibrium is what is called a stable equilibrium. This is what is called a stable equilibrium. If the same sphere is kept on a curvature upward like this, and then also I would call that as a equilibrium point. But this equilibrium is what is called an unstable equilibrium. Equilibrium. See, my stylus is slipping. Unstable equilibrium. So what do you mean by unstable equilibrium? The smaller disturbance that is acting on the sphere would change its state from this position, and then it cannot get back to this point called an equilibrium point. So here, this contact or this position is what is its equilibrium. Here also this is an equilibrium, but the small disturbance will take away your system from the equilibrium state, and then it is called an unstable equilibrium. And you see the same sphere, instead of on a curvature, if it is there on a flat surface, and that is called a neutral equilibrium. Neutral equilibrium. That means if you are disturbing this, it will go to a next state and that it won't come back. But that is what is called a neutral equilibrium, right? So it is not going to oscillate. You give an energy, it will change from this state to other state, but the datum is remain same in this case. And here the datum does change. If this is my reference and the datum here is this, that won't get back. And here datum would be ensured again. So this is what is called three types of equilibrium, and what is that we are going to be interested is understanding what do you mean by stable equilibrium and what do you mean by unstable equilibrium, and how can we bring in this unstable equilibrium to a stable equilibrium is what is very important. So you have to connect this fundamentals what you have learned in rigid body mechanics to our vehicle now. So look at this is our vehicle. So this is my rear axle, this is my front axle, the vehicle, and let me just have, this is its straight path, and this vehicle, CG location somewhere here, and if this vehicle is acted upon by a side force, wind gust, its resultant acting on this, so what would happen to this vehicle is what is to be looked at. If this vehicle is originally an understeer vehicle, you know that this will go away from this disturbance. If this vehicle is a neutral state vehicle, that means, and if it is going with a cruising speed on a straight path, so that is speed constant, it is again ensuring the static equilibrium. And this static equilibrium would be a stable equilibrium or an unstable equilibrium is what we have to understand. Or if it is of neutral equilibrium is what you have to understand. So if it is of stable equilibrium, what does that mean? This would have the tendency to go here, and the system dynamics of the system would always be looked at as a control system model. I'm going to introduce that in a while. And if you are introducing like that, you would always look at the response and then do correct your input accordingly. So if your vehicle, because of this side force acting, it goes like that, and it is feeling like an oscillation about its z-axis, vertical axis, right? It is in XY plane. This vehicle is in your XY plane, and the oscillation in XY plane about z-axis would be initiated, and by correcting your steering, you would be able to have a control of stable equilibrium. So that try to go here and come, like it will be oscillating. So the same, if your vehicle is of oversteered vehicle, we know that this would turn into curvature. So if the side force is acting, it would turn into the disturbance side, and that's oversteer tendency of a vehicle. At that time, even you are trying to correct your steering at particular speed called a critical speed, your vehicle do go an unstable state is what we have just uttered and understood when we were started our high speed cornering study. So that is your oversteer condition of your vehicle, and that would take to an equilibrium called an unstable equilibrium. That means this oscillation cannot be there, and suddenly your vehicle would be drifted and it will be spinning about your vertical axis, and the state would change, and the position of your vehicle on the road is arbitrary, and that is what is called an unstable equilibrium. So if a vehicle is unstable equilibrium because of oversteered tendency, of a vehicle. Maybe the vehicle is of rear engine mounted, rear wheel drive vehicle, naturally or oversteered tendency vehicle. And such vehicle, how do I ensure stable equilibrium is what is my objective of the study. So what is that vehicle parameters are going to be dictating the state of my stable equilibrium, or what is the state of my unstable equilibrium? So what do I change in my vehicle parameter that would ensure even the vehicle is of oversteer tendency, I would be able to have my vehicle under a controlled motion. So that would limit my vehicle speed or lateral acceleration accordingly. That would ensure always my stable equilibrium of my vehicle. That's what is the objective of our stability analysis that we carry out. So in a stability analysis, you would be able to ensure or predict the system with the parameter is of stable equilibrium, we can conclude. Or we can use the parameter and say that the vehicle cannot be under stable equilibrium. That vehicle would undergo an unstable equilibrium, like that you can comment. And also you can propose what would be the necessary input or the parameter change in your vehicle that can ensure the unstable state eliminated and stable state brought in, is what is that objective of our study, right? So this all to understand, again we have to look at this physical phenomena through mathematical equations, right? So for that purpose, I am just going to introduce again your bicycle model and then our necessary equations and to see them. And see here, what is another important thing is this vehicle stability analysis. Mathematically, if you look at it, it is nothing but an eigenvalue problem. So what do you mean by eigenvalue problem? Eigenvalue problem is there is no input to the system. The disturbance is because of some initial conditions alone. So you give some disturbance. You displace it at t is equal to 0. There is some displaced position from here to here, and then you leave it. And you are not going to give an external force, no, nothing. So it is purely an initial state, and the disturbance that is going to be looked at to look at the nature of your system, and the nature of your system would help us to understand the equilibrium state of your system and to comment on whether it is stable equilibrium or unstable equilibrium. So that is what is called an eigenvalue problem, where we will not give any input to the system. So the delta steering angle is 0, no input to the system. So that's why I just have taken this example that my vehicle goes in X direction in a straight path with a constant speed, and suddenly there is a disturbance that acts due to wind blow from side, and that would make my vehicle path how is what is going to be looked at. So this sudden disturbance would cause this vehicle to oscillate in this z-axis, about z-axis, and that's going to be oscillation in yaw plane. Yaw plane stability. So if this oscillation dies out immediately, and then I could have my vehicle control and go straight, no, this disturbance can be not having an effect on vehicle, then it is stable. If this yaw plane stability is not ensured, that means that oscillation would become higher amplitude, and particularly when the vehicle tendency is oversteered, pronounced due to this side force, and the state would be of the second case, and it cannot come back to its equilibrium position. So that is all happening in no time. That's not pronounced for a longer duration. No. The sudden wind blow, you are straight driving, suddenly there is a wind blow. If your vehicle is under control, that means it is under stable equilibrium. If your vehicle is gone all of a sudden, an unstable state spinning, then it is unstable equilibrium. So unstable equilibrium would happen mainly due to this oversteered condition, vehicle driven at its critical speed, and so on. That's where we are going to define something called the stability factor. So we'll look at what is stability factor, right? So this is what you have to understand. For that, let me just look at a system which would be a generic system, and what would be the base mathematics behind, and small bit of control system. So one should be, when you are talking about stability of a vehicle, it is a control system study. Of course, mathematically, it is solving differential equations and converting the differential equation into polynomials, finding roots and commenting on them. That's one side. But this all process of mathematical equation handling is to design an appropriate control system. And that is what is to the context of vehicle stability. So I would be talking bit on this control system as well, and your state equation. How do you get from your governing equation, and what is the advantage of state equation to get something what is called a closed loop transfer function, and if you have this transfer function, how do you get your stability factor and so on. So this associated maths is what I'm going to explain you. Of course, you have to go through if you are really wanting to pursue more in your vehicle dynamics extension as an automotive control system. You are recommended to learn textbook from a textbook called Modern Control System. Modern Control Engineering by Ogata. So this textbook, you can look at. It is very interesting textbook. You would see that a book for modern control system. Why is it called? Is because there is a conventional control system and modern control system. Modern control system essentially account your state space representation of your system, and that can be of linear system, and then a study of non-linear system. All that book, that itself is a course, but we will not be able to get all of them in our vehicle dynamics aspect. But I would just have to talk on some of the control strategies, especially in airplane stability when it comes. And I'm looking at instead of this is a 2-degree freedom model, so it is simple. If I have to work with an n-degree freedom model, then my governing equation would be an nth order ordinary differential equation with the multiple input given, and that input also can be represented by another differential equation, and then it has become more generic. And such time to handle the stability, the design of your dynamics, control dynamics, you require a control system. And you would study some criterion called stability criterion. In this case of yaw-plane stability criterion, one is called Routh stability criterion, and that is what we will look at it. And this all essentially in today's lecture, and maybe one more lecture I would take, we will look at yaw-plane stability. Then we will get into rollover stability, and that's where we will stop our lateral dynamics, and then get into longitudinal dynamics and tire mechanics, right? Yeah. So let me continue. So let us look at a general equation. General equation. This 19 square board is not responding. So let us look at a general expression. To represent a system, right? In general, a system can be represented by a differential equation of nth order. So I can have my system by nth order differential equation, ordinary differential equation. So let me just represent that as a naught d power n x by dt power n plus a1 d power n minus 1 x by dt power n minus 1 plus a2 d power n minus 2 x by dt power n minus 2 plus, and so on. I would end see n minus 2, it is going to be n minus nx, right? So it is going to be a n d power n minus n, this is going to be 1, so that's going to be x, a and x. And that would be equal to b naught d power m u by dt power m plus m b1 d power m minus 1 u by dt power m minus 1 plus and so on plus bm u, right? So this is our general equation or nth order system. Nth order system. So when you look at nth order system, it is difficult to imagine what would be an example of higher order systems, right? High complex dynamics that involve in satellite launching of your rockets can have an nth order system in it, right? But if you look at the same rocket motion in a trajectory, that would be confined to second order system. So if you are having a physical system as an nth order system, and that can be described by this equation 1, what is called an ordinary differential equation of nth order. So if you look at on left hand side, you have this differential form. On the right hand side, you have this form. And you have here this a naught, a1, a2 up to an. Similarly, b naught, b1 up to bm. So these all are called coefficients of this ordinary differential equation. If these coefficients happens to be constant, they are not function of time, then they are called the time invariant parameters, right? And if your system is called a linear system, that means that is depending upon only on an independent variable, not by any products of variables or no trigonometric terms in it, then that system is called a linear system by observation. And to understand more clearly what do you mean by linear system, if I have n number of inputs to the system, then I would have my responses for an individual input. If I give whatever that I have, if I add all of them, all the individual responses, that would be equivalent to that of n input response. So that is what is something called the principle of superposition that holds good for a system. Then the system is what is called a linear system. So our study of our bicycle model for airplane stability is linear time invariant system, LTI system we call. So in an LTI system, if I have to represent the system, I look at something called a box or a block called a transfer function. And this transfer function is what is say G of S. Right? We will see what is G of S now. So this transfer function is what is the block in my control design of my nth order system, if I say, and I would have there an input to the system, and that input would be normally through a point called a summing point in the system, and then it will be given here, and then you will take out. And you will have some points in the control design called branching point, and this is called the summing point, and this is called a branching point. And I'll take an output and then give that again into this as an input. And this feedback, whatever I take from here and give it to an input again, and that's why this system is called, control system is called a closed loop control system. This is called closed loop control system. Right. So what do you mean by closed loop control system? If I look at my vehicle and if it goes away from my path, in a case that we just have seen, where its behavior is understeer behavior, I could control, I could correct by steering action. If it is oversteer condition, then I counter steer and correct it. So I observe the output response and then do a corrective measure in my steering input, and then it comes, then it is an example of closed loop control system, right? So that's exactly what is that test popularly called double lane change test of your vehicle. So you are to overtake a vehicle, and you have to go in your track. So what do? You give a steering requirement, and then again you correct the steering, and then you are overtaking and going. So this is from the control feedback from your response of your vehicle. And one of the closed loop test is this double lane change test. You also have test something called a slalom test. So you will have the cones in the path, and you have to go as in a sinusoidal path. So you have to correct your steering and go maneuver nicely, go ahead. So there are many tests that are called a closed loop test. In our before part of CAD, we looked at open loop tests that are to find out its tendency, its natural behavior, and so on, right? So now you see this is simple representation of control block diagram. So I would have my input U of S, and I would have my output X of S. Right, so I have this feedback here, and this is what is essentially give. So here this feedback and this meet here, so this is plus and this is a minus here, and it corrects, and what I get here is correction signal. So E of S. So this is a simple representation of your closed loop transfer function. So this closed loop transfer function would be simply it is X of S, which is output response, by U of S, input response. So this is what is your closed loop transfer function. And this is simple representation of your dynamic system as a control system model. So in control system model, you'll have number of blocks, branch points, summing points like this, right? Okay, just keep that in mind. And now to have this closed loop transfer function, I look at this governing equation of nth order system, and I see in both sides it is an ordinary differential equation formed with the constant coefficients which are time invariant. So this represents my linear time invariant system. So right hand side, whatever that I have, RHS is input function, that is again in a differential form, and left hand side whatever that I have, essentially to understand the dynamics due to this input. So now how do I relate this nth order differential equation to get my closed loop transfer function? So I have to take Laplace transform on both sides of this equation 1 with the zero initial condition. So with the zero initial condition is very important point. And then whatever that I get can be reduced to this open loop, sorry, this closed loop transfer function. So then what would happen to this equation 1 will be this. So what is that I'm doing? I'm going to do taking, just it takes. This is hand, yeah. So I'm just going to do take Laplace transform on both sides, and my equation is going to be like this. So I would have my X of S by U of S would be now in this way. So if I apply that, taking Laplace transform with the initial zero initial conditions, and I would have my transfer function as the ratios of two polynomials, and the polynomials are b0 s power m, and s is Laplace variable, plus b1 s power m minus 1 plus b2 s power m minus 2 plus and so on, plus bm minus 1 s plus bm divided by, I will have this side denominator polynomial, because X of S and U of S would be common, and then I do this ratio, it's simple, and I will have here it's A0 s power n plus A1 s power n minus 1 plus A2 s power n minus 2 plus and so on, plus an minus 1 s plus an. So this is what is my transfer function. So the transfer function is now ratios of two polynomials, And if I call this transfer function as proper transfer function, then the condition of this order m should be less than or equal to m should be less than or equal to n, then it is called a proper transfer function. If m is less than n, then it is called a strictly proper transfer function. Proper transfer function. Strictly proper transfer function. Right? So now here you look at when I have to do my eigenvalue analysis. What do you mean by eigenvalue analysis? My input is 0. That means the RHS will be 0. My governing equation 1 will become only the differential form with the constant coefficients A0 to AN of nth order system equal to 0. So then I would have, by taking Laplace transform, a polynomial called characteristic polynomial, and I'll find out that roots of the characteristic polynomial, and looking at the roots, I would be able to comment on the vehicle stability or the system stability, in this case, nth order system stability. So what is that polynomial? The denominator polynomial of this is what is a characteristic polynomial. What is this is called? Characteristic polynomial of order n for nth order system. And in an eigenvalue analysis, in eigenvalue problem, this characteristic polynomial should be equated to 0, and that's called a characteristic equation. Characteristic equation, that is A0 s power n plus A1 s power n minus 1 plus and so on plus an equating to 0. So here it is of nth order. The roots of this polynomial are going to be n roots, and these n roots placement in your Laplace domain is what is going to be talking on your vehicle stability, right? It is hanging. Yeah. So look at this is my complex plane, and this is my real part, and this is imaginary part. Sorry, real part, positive real part, negative real part axis, and this is j omega, positive imaginary axis, negative imaginary axis. So if I have my roots always lying on this side, then it is stable equilibrium. If it is also lying on this axis, complex conjugates are my roots, then it is again going to be an oscillatory system. If these are not on this line, and so the roots lying on this axis, what it doesn't have a real part, it is having only imaginary part, and the imaginary part is complex conjugate roots. So that represent the system oscillation. If I have my all roots lying on left half plane, this is left half plane, and this is right half plane. Right half plane. Right half plane, I will have either real roots alone or a root to represent here have got a real part and j omega both. So the real part of the root ensures unstable state. Unstable state. Right, whereas the negative real part, this side anything lies, that's going to be a stable state. So now the question is, here I have an nth order system, I have nth order characteristic polynomial, and hence the characteristic equation eigenvalue analysis, and find the roots, and the roots finding, it's going to be tedious. So I can have roots which can be linear, quadratic roots, or higher order roots. So this I can partially factorize them as a linear factor or quadratic factor or cubic factor and so on, and then simplify them and find the roots. So it's a tedious process. finding all the roots and then commenting on the stability. So that is instead you are going to learn, maybe next class we will see that, called a Routh's stability criterion. Routh's stability criterion, wherein I don't require to look at the roots of this polynomial. Instead, I look at only the coefficients of this polynomial. And if the all coefficients are positive and there is no zero coefficient, that means here an should not be equal to 0. Then I can comment straight away on an absolute stability of my system. Right? So if all the coefficients are positive of this characteristic polynomial and there are no zero terms of coefficient, then I would comment on an absolute stability of the system, but still this is necessary condition but not sufficient, because though you have positive coefficient, there can be a chance of your system that can get into an unstable state. So how do you predict that without finding roots of this polynomial is what is proposed by Routh stability criterion. So we will understand that and then look at our bicycle model, which is second order system only, and that simple model, not an nth order system. And then we will talk more on this stability in the next class. So I stop at this point. So I just have done in this particular period recapitulating what we have learned in last 30 lectures. And then what are the remaining part of our course ahead of learning in another 15 lectures. And I'll spend maybe 3 to 4 lectures on the stability of your vehicle in yaw plane and rollover stability. And then we will get into longitudinal dynamics and tire mechanics to substantially support our content of the syllabus and learning of this course as a whole. Right? And today particularly just got to introduced with what do you mean by stable, unstable equilibrium that we talk. What do you mean by unstable state of your vehicle in yaw plane model? And how do you look at generic and nth order system by governing equation? And this governing equation of this kind represented by Roman letter 1, how do you connect to simple representation of your control system design? And then looking at your closed loop transfer function of this governing equation simply by taking Laplace transform on both sides of the equation number 1 with the 0 initial conditions, and then you were able to get the expression of your closed loop transfer function as ratios of two polynomials, order m and order n. And then we called a strictly proper transfer function. The polynomial order of numerator polynomial order should be smaller than that of denominator polynomial order. And also we have stated that the denominator polynomial would be called a characteristic polynomial, and that would act as a characteristic equation when you look at an eigenvalue problem wherein you impose an initial condition only there and there is no input to the system. That's exactly what would be our vehicle subjected to a wind gust. So there is no input that you are giving, there is no steering input by the driver to the vehicle, and the vehicle is driven straight and there is suddenly a wind gust come. And then the expected oscillation of your vehicle for a moment would happen, and that would ensure the stable equilibrium. But there can be influence of your vehicle parameter, and that can take that to an unstable state. So yaw plane stability is what is our focus of study in the next period, and then we will go for rollover stability analysis. And with that briefing, I stop today's lecture. If you have any doubt, you can ask. And your CAT 2 answer script will be ready for this weekend, right? Okay, good day to all of you. If you have any doubts or anything, you can ask. Otherwise, I will end the meeting now.